Okay, now I think we'll go ahead and get started. Welcome, everybody. I'm Mike Riddle, Executive Vice President here at InCab America, and this is ADSS Engineering 101. We are registered with RCEP, the Registered Continuing Education Program, and so you can get professional development hours or continuing education hours through RCEP from this class. This does not mean that RCEP in any way, shape, or form endorses the content of this class. It just means that we've met their standards and are able to give you guys credit. So the purpose of this course is to discuss the 8 important design elements of all dielectric self-supporting cable, ADSS. We're going to go through the jacket configurations that are available, the materials that can be used for the jackets, the materials that can be used to give the cable its strength, design of the optical core, design of the tubes, and really that means tube material, the number of fibers per tube, actually tube material down here, tube design, yes, and then outer jacket adhesion to the strength material. So we got some topics here that are controversial, meaning that I work for InCab and we make ADSS cables this way. And some other fiber optic cable suppliers may make it a different way. And we would disagree with each other about how they should be made. I am going to try my best to present both sides so that you understand the trade-offs that are involved, because in the real world of engineering, almost everything involves a trade-off of one form or another. So we're going to discuss the ones that are controversial, and the goal is for you to understand what the controversy is all about, and then you can look at your situation and make an informed decision about what you want to do for your cable. Then we're going to do a little bit more about how tubes and optical cores should be made and why this is important for long-term performance. And then we're going to touch on just a brief primer on sag and tension for ADSS cables and how to determine when you need a track-resistant jacket. Again, these will be primers just to touch on it, and they both will be the subject of further webinars in the future. So here are the learning objectives. They flow directly from the purpose. We want you to learn about these 8 design elements. We want you to understand how tubes and the optical core should be made for good long-term performance. We want you to understand the basics of sag and tension. And we want you to understand when you need to think about a track-resistant jacket, when it may be necessary. So, ground rules here. This is the introduction and sound check. If you're hearing me, all is well. Then the actual presentation should take about 75 minutes. And for that reason, you will get 1 1/4 professional development hours if you want them. We'll talk about how to get those at the end. After the presentation, we'll have a time for questions. And I think today we're going to allow people to actually speak for their question as opposed to typing it in chat. We're going to try that. And during that question and answer, please keep the questions pertinent to the topic. So like if you've got an order in progress or some business in progress with InCab, we don't need to talk about that. That should be outside a webinar like that. And that sets the ground rules. So let's get going. So to begin with ADSS cable, we need to review some basics. We need to things you probably already know. We're just going to review them very quickly, and they're important for understanding certain aspects of ADSS design as we continue through the presentation. And these entry principles are important for any cable. So ADSS, OPGW, duct cable, it doesn't matter. These basic principles apply to any type of fiber optic cable. Those are, first up, fiber. So there are lots of different fibers that are available today, but with ADSS, and incidentally also with OPGW and the electric utility industry, the overwhelmingly most commonly used fiber is low water peak single mode fiber. That's just what it's known. In Fiber 101, we will discuss why it's called low water peak. The governing standard is an international standard, and it's ITU-T G652, and it's table D. That's what's most common internationally today. An example of that is the Corning SMF28 family of fibers. An important thing for you as a user to know is that fiber from different fiber suppliers, so Corning, OFS, and others, are generally splice compatible in this fiber classification and good for around 60 to 90 miles. Again, the overwhelmingly most commonly used fiber type. And in ADSS, I won't even bother to talk about non-zero dispersion shift-hit fiber, other than to say it exists. I hardly ever see it used in ADSS. I actually can't even remember one time off the top of my head. I suppose if I looked, I might find an example of it, but very rare is the takeaway. Do see a little bit of multimode ADSS, but again, I'm not going to talk about it. If it comes up in your application, reach out to us and then we can discuss it in more detail and help you out with it. Okay. Then of fiber, the most important performance characteristics of fiber is its attenuation. And attenuation is the loss of power over distance. It's typically expressed in dB per kilometer. That means that when you input the signal, you have a certain power. And then over a distance, you receive at the end less power. So that's expressed as a loss of dBs, decibels per kilometer. Now, the kilometer isn't important. What is important is it's dB per length. So the length could be miles. So you could say dB per mile. So you could say dB per 1,000 feet. You could say dB per furlongs if you wanted to. It's loss over distance is the important concept. Chromatic dispersion, again, topic for another day. Usually not terribly important with ADSS because this is a long distance phenomenon. In other words, it becomes a problem when distances get great. And a lot of ADSS is often not used over as great a distances as OPGW and some other types of fiber optic cable. So you don't see chromatic dispersion be much of a problem when it comes to ADSS. So you're back to worrying about the attenuation is where you need to put your focus. Okay, next up under cable basics is the loose tube concept, because 99.99% of ADSS that's used in the world today is loose tube construction. The option would be tight buffer construction. I won't talk about it though, because as I say, the overwhelming majority is loose tube construction. And in the loose tube design concept, the fibers are placed inside a tube with a sinusoidal shape to them. And that means that you have slightly more fiber length per unit length of the tube than you do of the tube. Typically, it's going to be around 0.25%. It could be a little bit more. It could be a little bit less. And the reason to do that is that when the tube begins to elongate, which could be as a result of temperature changes or tension that can result from ice and wind loadings, And in aerial cables, and in particular with ADSS, it's not the temperature that's a problem. ADSS by its nature doesn't really change its length much in response to changes in temperature, which is a big contrast to OPGW. Metal cables change their length a lot. They have a very high thermal coefficient of expansion. ADSS and dielectric types of cable have a very low thermal coefficient of expansion. So for them, the tension is the result of wind and ice loading. In any case, when the cable or the tube begins to elongate, at first what happens is this sinusoidal shape just begins to flatten out. Now, it can only go so far before this ratio shrinks to 1. And at that point, the fibers are beginning to experience some of that tension that's on the cable. Fiber is very strong, but it's glass, which means it's very brittle. And so to the extent that you can, you want to minimize any tension on the fiber, and that's generally referred to as fiber strain. So to continue, important concepts that flow from this are the extract fiber, this 0.25% I talked about, is called excess fiber length, EFL. And as I say, it's that extra length of fiber per unit length of tube or cable. So there's the sinusoidal shape that you get in the tube, plus if you take a tube and strand it, like you see in this illustration, you put a helical shape into the tube, and that has the effect of increasing the EFL further. So I can get about 0.25% plus or minus in the tube. From stranding, I can get 2.5%. So basically a factor of 10 more. Just for reference later, because I think it comes up later, lay length, when you strand an element, is the distance it takes for that element to make a complete 360 around whatever you're stranding around and get back to its original position. And in an ADSS cable, that thing you're stranding around is generally the center element. Also from this, you get zero fiber strain margin, and that's the point when this ratio has gotten to 1 and the fibers are beginning to experience strain. It's usually expressed in terms of percent of the rated breaking strength of the cable. Please keep these concepts in mind. They'll come up later in the presentation. Some basic things that you can take away from this concept is that if I put too many fibers in a tube, then they can't have the sinusoidal shape, right? Physically, there's only so many fibers that you could put in here before they're sort of forced to be straight. And that's overfilling a tube, and that's not good. Bundling or binder threads are a concept that you need to understand, because as fiber counts have increased in cables, so I've been doing this for a long time, since basically the early 90s. And in the early 90s, an 8 fiber cable was a high fiber count cable, and a 12 fiber cable was wow. These days, we're regularly doing 144, 288. We've even done some 432, and there are even higher counts in use in the world today. So fiber counts have gone up in the tube, and then it runs into a practical problem in the field, and that's how the splicing techs distinguish one fiber from another. So beyond about 12 different colors in the field, it becomes very difficult to distinguish those colors. So what do? Well, 2 things have been developed. One is bundling, or this binder threads, as I call it. These are the same thing, where you take a group of 12 fibers and you wrap a color-coded thread around them. That's good. It allows you to quickly separate different bundles of 12. There can be a problem, though, if you lose track of that binder thread or the bundling thread, and then you have to start over. So the other technique that is used is ring or band marking. In ring or band marking, you use typically a black mark. So you go through the 12 fibers and then you repeat them with a black mark. And that has certain advantages to it. Sometimes you can use both, but in today's manufacturing environment, what you see here is realistic. Today's manufacturing, each fiber has the same amount of sinusoidal shape to it, and they're all in phase, so they're in together. Again, back when I started in the early 90s, we had more loosey-goosey loose tubes, where maybe there would be a fiber that would be out of phase or another fiber that would have a different amount of EFL in it. But today, because the fibers are well coordinated, so they're consistent and well coordinated, each fiber has the same amount of EFL, and all fibers are in phase, bundling works well. You're not really going to have a problem. The entire bundle moves as a unit, like you see in this illustration, even though no binder thread is shown on it. They all move together. So it works well. Okay, ADSS. One of my pet peeves is people that use the term ADSS to really mean any kind of dielectric cable. So whether it's underground cable or lashed cable or really real ADSS cable, they use the term ADSS. ADSS means all dielectric, self-supporting. So dielectric means no metal components. So a armored cable, using corrugated steel tape armor, is not an ADSS cable because it has metal in it. A duct cable or a lashed cable is not an ADSS cable because it's not self-supporting. Self-supporting means it's designed to support its own weight. So again, maybe I'm being pedantic, but I prefer the precision of using ADSS when you really mean ADSS. The US standard for that is IEEE 1222. The international standard is IEC 60794-4-20. They're pretty similar in their requirements. People in our industry, again, another Mike Riddle pet peeve, often talk about short span ADSS, medium span ADSS, long span ADSS. And I also hate that because that's very vague. What exactly is a short span ADSS? You know, to me, short span is 200 feet, but maybe to you, it's 400 feet. And doesn't matter if it's 200 or 400 feet. What really matters is your sag and tension characteristics, and those are also a function of your loading district or your loading conditions. So, how much sag are you willing to allow under what condition? That's going to determine whether a cable is really suitable for a so-called short, medium, or long span application. So I really don't like these terms. They really are vague and have no real meaning in it. We will talk about sag and tension later in the presentation, as I've said before. All right, so now we're up to the hardcore content. What's actually going into ADSS design? I mentioned we have 8 elements, and it's going to seem like, wow, so many choices, too many choices, because for every one of these design considerations, there are at least 2 choices, sometimes 3 or more. We're going to talk about each, so relax. It's going to be real simple. You're all going to be experts at the end of this webinar. First up, jacket configuration. You got 2 choices, basically, double jacket or single jacket. Double jacket is like what's shown in this picture here. So I have an optical core, loose tubes stranded around a center element. And then there's a jacket applied over that. And then the strength material is applied over that first jacket, which is generally called the inner jacket. And then you have an outer jacket applied over the strength element. Pretty simple. This is a traditional design. So when ADSS was first introduced, they were double jacket designs. It has certain advantages. It has excellent reliability because this inner jacket is protecting your optical core. And you can also do very long spans with this construction. In fact, at some point, your spans become so long that you have to use double jacket construction. But it does have disadvantages. It is going to be more expensive than its alternate, which is a single jacket design, in the range of 5 to 25%, depending upon the fiber count and the specifics of the cable design. And you are inherently increasing your diameter and the weight of the cable. So higher diameter means there are effects of that. So higher diameter, shorter available reel lengths, which might mean more splice points, all else being equal. The hardware gets bigger and has more metal in it, so it can cost more. More structural loading as a consequence of the weight. Plus the diameter means more wind loading as well too. So there are disadvantages to this design configuration. Single jacket, relatively newer, but it's still been around for more than 20 years. Its advantages, you're reducing the diameter and weight, and you're saving money as a consequence of that. But the disadvantages that flow from these are you're reducing your reliability because you've eliminated that second jacket, and you are limiting your span lengths and or your loading conditions. So I say here less than about 650 feet, a rough guideline. As I say, a guideline, not some kind of hard rule carved in stone. So what should you be doing? Well, turns out the optimal choice, there isn't one. It depends upon what you're trying to do, what your goals are. I think you should use double span if any of these conditions apply. So if you're over 600 feet, I think you're better off going with the double jacket construction. If you're in an NESC heavy loading district or something similar, right, for our, those outside the United States, you're going to have your own loading conditions. And if they're along the same lines as the NESC heavy ones, or if you have extreme ice and wind loading, yeah, you should stick with the double jacket construction. When your fiber count gets above 144 fibers, double jacket, I think you need. And if you're, if you're really putting a premium on reliability, double jacket construction is where you ought to go. Single jacket construction is appropriate if all of the following apply. So if your span's less than 600 feet, if you're in a light or medium conditions and you don't have to worry about extreme ice or wind loading, when the fiber count is less than or equal to 144, and when good reliability is good enough. This is an appropriate solution. The economics in the long run can work in your favor. The money you save up front versus the money that you have to spend later to maybe replace some cable that's had some problems. So next up, the jacket material itself. What do you make it out of? You've got two and sort of a third choice there. So first up, high density polyethylene. The advantages to it are that it is very tough and durable. Does have some disadvantages though. Over time, in an aerial environment, it is more susceptible to cracking. Its own density sort of works against it in actual environmental conditions. It does make splice prep significantly harder, and it does cost you more money. So it's harder just to get through the jacket. You can really feel it. Medium density is the first up alternative, and its advantages are it's still tough and durable, arguably less so than HDPE, but still tough and durable. It helps facilitate cutting through it during splice prep, save a little bit of money. but that disadvantage is it's not quite as tough and durable as HDPE would be. And the third choice is low density polyethylene, but I would never, ever use that on the outside of the cable. It's a great choice for your inner jacket, but as I say, never, ever for an outer jacket. So what choice to make? Probably guessed already. Medium density polyethylene is the best overall choice for the outer jacket because you're balancing the toughness and durability with your cost and ease of splice prep. An excellent solution here. Low density polyethylene, as I already said, well suited for an inner jacket. Now, if you came to me and said, well, I want medium density for the inner jacket too, we would say, certainly, no problem. But if you ask me my recommendation, I think this is a good choice for your inner jacket. Next up, what strength material do you use? Now, this topic may be a surprise to a lot of Americans because in the United States, you only think about Kevlar. Kevlar is really the trade name from DuPont, who invented that. The more generic name is aramid. It is the original and still most used strength material that's available today. But you're surprised to know there are options. So we'll talk about the options, and there are actually two of them. The advantages to aramid is very excellent strength. It's got a high strength to weight ratio, 5 times greater than that of steel. It has excellent thermal stability. It's stable way above and below the range of ADSS in its operational life under field conditions, way above and below. Because of these two properties, you can easily limit fiber strain. Remember, we talked about that. You want to avoid strain on your fiber as much as you can to maximize reliability. And so you can limit fiber strain or even eliminate it totally at the maximum rated design tension of your cable. This is the maximum tension that you're expecting the cable to experience under field conditions, so under wind and ice loading. And you can easily keep fiber strain to less than 0.2%. And this is considered the best maximum limit. So let's talk about that for a minute. It's better if you don't have fiber strain at all. But if you do choose to allow it, and we'll talk about why you might want to do that later, this is a good limit to use. It comes from research that Corning did in the late 80s, early 90s time frame. And basically they said, if you're going to allow strain on your fiber, this is what you should keep it to to have an acceptably low risk of failure. Disadvantages of Kevlar or aramid is that it is more expensive than the other two options. It can also become conductive in the presence of water. So if you have a jacket breach and water is getting inside the cable, and you have an electric field, so you got to have both, you can have some problems. What causes jacket breaches? Shotgun damage is number one. Number two is rodents, including squirrels. Also, like large birds of prey have been reported to perch on a cable and their talons can pierce the jacket, or they can lay prey on the jacket and then peck at that prey and therefore breach the jacket. So that's your entry point, but you got to have the electric field too. Your other choices for strength material are fiberglass yarn, and it's a lot less expensive than aramid, and rodents don't like chewing on it, including squirrels. So if you replaced aramid with fiberglass, you can easily get a C rating. So I'm talking US grade school, A, B, C, D, or F. You can get a C easily using fiberglass yarn. But it's a lot lower strength and less thermal stability compared to aramid. And so you have to use more of it to get a certain strength. And that tends to drive up your overall diameter. So the cable diameter is going to go up around 10, 20%. And because of its properties, you're going to end up with typically higher fiber strain at that maximum rated design temperature, design tension. So instead of 0.2, which is like where you would like to keep it, you're going to be taking a little bit more design risk with fiber strain in the range of 0.3 to 0.4%. The strength material, your last choice is fiberglass reinforced plastic rod, so FRP. So the same material that you use in the center, you can take and use enough of it to get strength to the cable to make it self-supporting. The advantage of doing this is that rodents, including squirrels, hate chewing on it. So you can get an A rating by using this material. Now, if you do that, they've already cut through your jacket. So you do already have a problem, but what you can do is add a rodent deterrent additive to the jacket and further discourage them from messing with your cable. And you can increase this rating from an A to an A+. You're also increasing your crush resistance. You've got a very versatile cable as a consequence of this design change. So you can use it as a direct buried underground cable too, which is excellent. Now, I had some hopes. Remember I said before, the #1 field problem with ADSS has been shotgun damage. The #2 has been the rodent damage. I had hoped that maybe this construction would be more shotgun resistant. We did some testing. Unfortunately, no. Not any significant improvement over a double jacket, standard double jacket construction with aramid. Disadvantages of this approach is it's expensive. You're driving up your cable diameter because of the geometry of these rods, and you have to have an inner jacket when you're working with the FRP rods. You're limiting your spans. You can still get pretty good spans, like 1,000 feet should be no problem. But you're increasing diameter and weight considerably. And then you got to cut off all of these during splice prep. And so that's going to make splice prep a little harder. And I made a comment here, enjoy the next slide when we think about critters. So here's what they actually do in the field. And I will note, this was submitted to me as a example of critter damage, but the more I look at this picture, the more I wonder if that's not actually shotgun damage. But anyway, it could have been somebody shooting at a critter on the cable. And then this picture just amuses the heck out of me. I do not understand what this little guy was thinking. Okay, so we've talked about the 3 choices for strength material. What should you use? And this is another example of the optimal choice depends upon what you're doing. Aramid should be your default choice. Really, you should use fiberglass or FRP rod in special cases. So fiberglass, if rodents are maybe just possibly a problem, or they're just more of a nuisance problem. And I mentioned before, you can add a rodent deterrent to the jacket material, and you can up your performance there. You should also limit it to short to medium spans. And I know I said I don't like these terms because they're vague, but they do give some descriptive ability. But more importantly, when you're trying to cut costs to the bone, when every penny counts, fiberglass could be a good option. And today, a lot of utilities are doing fiber to the home projects, and you have to do drops to individual houses, and you're really trying to keep that drop cost down. Fiberglass can be a good solution to that. You're absolutely trying to cut costs to the bone. FRP rod is really a special case. You really need to use it when you know you're having problems with rodents, especially squirrels. But you do have to double check that the sag and tension characteristics for it are going to work for you. Again, you can add the rodent deterrent to further discourage the critters from chewing on your cable. And this might be an option also for the flat drop cables. Often butterfly cables are essentially a variation of this concept. All right, next up, core design. Core design. So the optical core is comprised of the tubes that are stranded around the center element, typically an FRP rod. As a consequence of that, you end up with these little gaps. Well, what do you do about these gaps? Well, first up, why should you worry about the gaps? Well, because a jacket breach. If the jacket get breached, and we've already talked about the causes of them, water would get inside. If water gets inside, in an ADSS cable, it's going to tend to migrate towards the belly of the span, the low point of the span. And then if cold weather comes and freezes, well, the water expands when it freezes and it'll crush the tubes and it'll show up as attenuation changes, or it might even be able to break some fiber. So bad things happen. So you need to try to do something about the water if it gets inside. And you've got two choices. You've got a dry choice, which we'll talk about first, but you've also got a wet choice where you flood these, you fill these interstices. So dry, we're going to talk about first because it's become the norm in the United States. It's newer, but again, relative terms, still over 20 years of use. And what you're doing is you're laying water absorbing yarns, which use super absorbing polymer, SAP, to absorb any water that gets inside the core. So the advantage here is that makes splice prep much easier, less messy, because you're not trying to clean this gel off the tubes in order to work with them. Saves a little bit of weight. I think it's kind of debatable whether it's significant. Begins to get significant certainly at higher fiber counts, but so for me, kind of a low advantage. But a big disadvantage, and that's that water is getting inside the cable before it gets absorbed. So the water is already inside the jacket before your super absorbing polymers get to work. So the alternative is a flooded core or a wet core. And like I say, that involves using gel to fill these little gaps. Basically the same gel you use inside the tubes. That's the original concept. But in the United States, that design concept has been totally replaced by dry core. The advantage, as I mentioned already, dry cores let water get inside, but wet cores keep water 100% out. You've got an immediate barrier. The water doesn't even get inside the core. And it turns out this design concept is slightly cheaper. It actually saves a little bit of money. But it comes with a hefty disadvantage, and that's the messy splice prep, because you're typically working with 6 feet, 2 meters or more of core that you have to prep. You have to remove the jacket, remove the tubes, and that process just creates a huge mess. So in the United States, you see basically zero flooded cores in the United States. Outside the United States, you still do see it. Technically, let's go ahead to the next slide. What should you be doing? In an ideal world, I would say use the flooded core, but in the United States, if you tried using a flooded core, you'd probably get fired. So in the United States, it's really your default choice. You're just asking for trouble to use something else. Wet cores are still used in countries outside the United States, and I think it's great. As I just say, technically it's better, but in the USA, splice techs hate it, and it would just cause you trouble, a lot of headache if you tried to use it. So I got to say, stick with the dry core, especially if you're American. Okay, now I mentioned at the beginning that some of our topics are going to be controversial. This is the first of those controversial topics, where cable suppliers in the same room could actually come to physical blows over these topics, but I'll do my best. First up, tube design, dry tubes versus flooded or, again, wet tubes. Just as with the core, you're using a water swellable yarn. Yes, some of you may know. In the early days of this design concept, they would actually use the superabsorbing powder in the tubes, but today's implementation, it's a water swellable yarn to absorb any water that gets inside the tubes. It's newer, but it still has a pretty lengthy track record of 10, 15 years, maybe even a little bit more. The claimed advantages. So here you're going to see Mike Riddle's personal bias become blatantly apparent. It's claimed that, like with the core, it's making splice prep less messy. However, this is debatable because I've actually had splice techs tell me that the SAP residue from the yarns actually gets on the fiber and has to be cleaned off, and it's actually harder to clean off than the gel. The other claimed advantage is that it's lowering weight. And every time I've seen this, it's like on the order of 10 pounds per 1,000 feet kind of thing. So I think the weight savings may be trivial. Again, my bias blatantly coming out. Let's talk about the disadvantages. Water gets inside the tube before it gets absorbed. So you got that same problem that you had with the core with the tubes. But in the core, the only thing the gel was doing was keeping the water out. The gel, that was the only purpose it served, was to keep water out of the optical core. In the tube, the gel does a lot more than just keep water out. In the tube, the gel is helping the fibers keep that sinusoidal shape we talked about at the beginning. Yarn doesn't. The gel also helps the fibers move in unison with the tube during changes in elongation. So as the tension changes in response to wind and ice load changes, the tube stretches and the gel keeps the fibers moving in unison with the tube itself. There's a mechanical coupling there, and yarn doesn't do that. And as a consequence of that, in dry tubes, the fibers will tend, in dry tubes in ADSS in particular, will tend to flatten in the middle of spans and bunch up at the ends. And as a consequence of that, you get pistoning inside the splice enclosures. And it does cost a little bit more. So let's talk about that bunching up thing. So what happens is the tube elongates, the fibers flatten out. But then when the tube contracts later, when that wind or ice loading is no longer present, the fiber doesn't move back. Instead, in the middle of the span, it ends up trying to stay straight and pushes itself towards the end. And so at the ends of the spans, the fibers begin to bunch up. That continues down your structure, and the fibers end up pushing out of the tubes. And that's what you see in this picture here. The fibers are a mess now. Look how much they have pushed out of this cable. And this is often called pistoning. So your other option is the traditional flooded or wet tubes, where you're using gel to fill the buffer tubes. It's the original design concept. It's still the most common around the world. And as you can tell, Mike Riddle's opinion is obvious at this point. I think this is the better way to go. It keeps water 100% out of the tubes. So right off the bat, that's better. It's cheaper. It's helping the fibers keep their shape. It's helping them move in unison with the tubes during changes in elongation. So the fibers stay where they should be and they resist pistoning. And as an extra special bonus, the gel also helps improve the crush resistance of the tubes. It helps them resist any deformation. And that's good. The disadvantage is it's perceived to be messy during splice prep and to add time. But I think this has to be viewed in context. When you're working with tubes, you're prepping much less of the tube. So I really dispute that it's really that messy. And plus, cleaning the fibers adds like 15 seconds. You can go on our website. We have videos of the splice prep process. You can time it yourself, how long it takes the technician to remove the gel. And I want to keep that concept in mind because we're going to come back to time savings later in this presentation. So what should you use? I think I've already made it clear. I think flooded tubes for ADSS are the way to go. I think dry is fine for underground cables or if you're lashing a cable. But if it's an ADSS cable or an other aerial cable, and I'm specifically referring to OPGW, it needs to be flooded tubes in my estimation. Fiber counts per tube. You've got several choices there. The most common are 12 and 24, but we're going to talk about the others. 12 fibers per tube is the industry standard practice for decades. Everybody knows it and is used to it. It works well with taps. With ADSS, you're often having to tap to go serve some other area. And it lends itself better than 24 fibers per tubes. But disadvantages, you're increasing cable diameter and weight, especially as the fiber count goes higher. Therefore, you're increasing cost and you're adding more time for splice prep because more tubes have to be prepped. 24 fiber tubes is newer, but again, been around for a while. And you see its use more and more as fiber counts have gone up. It does decrease cable diameter and weight, especially at the higher fiber counts. It helps a little bit marginally, maybe at 48, but it helps a lot at 288 because at 288, you would have 24 times 12, 24 tubes at 12 fibers per each versus, 12 fiber or 12 tubes of 24 fibers each. That higher tube count drives up cable diameters a lot. It also drives up cable cost. You're reducing your time for splice prep. And 24 fibers does coordinate well with most splice trays, most, but not all. So disadvantages, you do have to check to make sure the trays that you're using can hold the 24 fibers. Again, many do, but there are some that are limited to 12. And it's not as conducive, it should be conducive to taps as 12 fibers per tube. And if you're doing a fiber to the home project, 24 fibers per tube may not work well with your network architecture because of how your optical splitters work. There are other counts available, and I just want you to be aware of it. So a 48 fiber cable most commonly would be 4 by 12. 2 by 24 is possible and maybe not bad, but you could do 3 by 16, 6 by 8, 8 by 6, or even 12 by 4. Of these, 16 fibers per tube is very uncommon. Likewise, 4 fibers per tube is not common, but 6 by 8 and 8 by 6 are not too bad, especially in the rest of the world in particular. Not so common here in the United States, but they do exist. And at 48 fibers and below, 8 or 6 can actually reduce your overall cable diameter. The reason is that typically the element count, if I go back to one of my pictures here, the element count is 6, like what you see in this cable. So specifically, this is like a 4 by 12 construction, and then I have 2 filler rods. Well, these are just wasted space. So if I put only 6 or 8 fibers per tube, I could use a smaller tube, and I would use all 6 positions here, and therefore I could reduce the diameter. So you can actually reduce your diameter at a relatively low fiber count. Obviously, that begins to work against you pretty much above 48 fibers, but the 8 or 6 fiber construction can facilitate taps, mid-span access, and it coordinates very well with a lot of fiber to the home network architectures that are used today. But it's not the norm. This is a little bit of an example of the chicken and the egg kind of phenomena, that if more people were using it, it would be more readily available. Right today, it might not be in stock at a nearby distributor, or I, as a cable manufacturer, have to go and make it. I don't have any materials on hand or cable in inventory like that. But if more people were using it, that would change quickly. Does increase your costs, right? Because making more tubes does make the cable cost a little bit more. And you really wouldn't want to do this much above 48 fibers, although I have seen it done. What should you use? Doesn't really matter, kind of up to you. Any of these are appropriate. Tube materials. So this is another controversial topic. The two most commonly used materials are PBT. I won't even attempt it. Well, I will attempt. Polybutylene terephthalate, PBT, versus polypropylene. PBT has high crush resistance, so it's about 60% greater in a cable with PBT versus cable with polypropylene. Excellent durability. These features make the cable work well with the dead ends. And remember, with ADSS, you've got a system, and the system is only strong as how well the two components work well together. So you have to have the cable, but you got to have the dead ends, and the two got to work together. PBT has good strength and excellent temperature resistance. Again, way above and below the range that you would expect an ADSS to be operating in. But does have some disadvantages. It's more easily kinked, which means you got to be reasonably careful during your splice prep. And it is more expensive, actually. Your other choice is polypropylene, and it is very flexible. So tubes are less likely to kink when you're working with them and trying to get them into your splice enclosures. And as a consequence of that, splice techs like it a lot. It is cheaper, but it does have lower crush resistance and tensile strength. It's not as durable as PBT, and you have much lower temperature resistance, especially at low temperatures. So by the time you're getting down into the minus, zero, getting close to 0 in Fahrenheit, or getting close to minus 20 in Celsius, you got to be concerned about PBT holding up. And it's not necessarily that you're going to get an immediate failure. What you could get is degradation in the tubes. And then this winter, it's okay. And for those of you that don't know, I live in Texas, and we had a really bad winter this year. So maybe it passes and survives this winter, but then maybe next winter it doesn't, or in another year or two. But in any case, you're potentially compromising your long-term reliability of your cable, which is another way of saying you might not get the 20 or 30 years operational life out of the cable that you expected with this material. Something I made a mental note of, but then forgot to actually put it in the presentation, is that PBT during splice prep also breaks cleanly when you're entering into the tubes. That's an advantage for it. In contrast, polypropylene tends to tear. So you don't get a nice clean edge on the end of your buffer tubes. And so that's a disadvantage for polypropylene as well. So what should you use? I think I've made it clear where I fall on this. PBT, I think, is the better material to use. And some manufacturers like us use PBT, and then others use polypropylene. So obviously those manufacturers would disagree with us, but we do have some allies that would agree with us on this point. And last up of our controversial topics is jacket adhesion to the strength element. You got two choices, coupled versus decoupled. In a coupled design, the outer jacket will have some adhesion to the strength material beneath it, whatever it is, aramid, fiberglass, or FRP rod. And the advantage is that this construction ensures that the tension and the strength material transition smoothly through the jacket to the dead end, because you got to think of the physics here. What's going on? You've got tension in your strength element. It's carrying the load. It's got to get to the dead end, which is connected to your structure, the pole, whatever it is. And to do that, it's got to go through the jacket. It's got to pass the transition through the jacket. So when you use coupled construction, you're ensuring that that transition occurs over smoothly and over a greater distance. And that helps you prevent jacket failures. And it also permits you to use shorter dead ends, all else being equal. The disadvantages, though, are that it does make removing the outer jacket less easy. And so splice techs may complain. You can mitigate that, though, by using 2 ripcords under the outer jacket. Your other choice is a decoupled design. In a decoupled design, the outer jacket is the opposite. It has no adhesion, or almost no adhesion, to the strength material that's beneath it. And in some cases, a manufacturer will even apply a polyester tape specifically to prevent adhesion. So they'll apply this tape over the strength element between the strength material and the outer jacket, specifically to prevent adhesion. And that does make splice prep easier, because it makes it easy to remove the outer jacket, but it is disrupting that smooth transition of the tension and the strength material through the jacket to the dead end. And as a consequence of that, you can get to stress concentrations, and stress concentrations can lead to jacket failures. Now, the cable suppliers that would do this, they will say, well, you just have to use a longer dead end. And they're strictly speaking, that's true. You are compensating for this design aspect by making the dead end longer to give more distance for that transition of strength to occur. But there are negative consequences of just making the dead ends longer. One is it increases their cost. And 2 is that if the dead end gets much longer than about 4 feet, your installers are not going to be able to install it from the pole, which means you're going to have to use a bucket truck or some other means to get the dead ends in place. And that in turn means more cost. So it's not a free solution just to make the dead ends longer. There are consequences of that. And I want to actually use some real world data. So at InCab, you can tell already that we use the coupled design concept. Some of our competitors, and again, some of our competitors would agree with us on this point, but some would use the decoupled design concept. So for a cable with the strength maximum rated design tension of 2,500 pounds or 12 kilonewtons, a coupled design, you can use a dead end that's 41 inches long. In a decoupled design, it's 48 inches. And then look at, as the strength goes up, notice how the dead end length gets longer. Now, I want you to pay attention to this, because the difference at these 2 strength levels of 4,000 and 7,500 pounds, 50% longer. So you've got an almost going on 8 feet length dead end, close to 8 feet, close to 9 feet here. Wow, 50% longer than what you need here. Why is this one, though, 16%? I really puzzled about that and looked at this number. And the more I thought about it, I really wonder if this supplier made a decision to not allow the dead end to be more than 48 inches just so that it could be installed from the pole. Because this is kind of more of a bread and butter type design here. And they might have decided to take a little bit more risk in their cable design in order to make sure that the dead ends could still be installed from the structure, so they didn't have complaints from their customers. Don't know that. A little bit of conjecture there on my part, but I just wonder. Anyway, in a lab, here's a jacket tear. on a known decoupled design, and note how the aramid is like pristine. So the jacket and the aramid beneath it were just able to move relative to each other quite easily. And so the jacket just slips right off, tears right off. You also see something similar in the field. Don't know 100% that this was a decoupled design, but the kind of the giveaway here is how smooth the aramid is after the break. Note the necking down as well. Okay, I think you can already guess what I think. InCab recommends the coupled design concept. Now, short spans, yeah, okay, maybe you can get away with this. Maybe I'm being a bit of a purist here, but I prefer this. Short spans, yeah, maybe. Again, some manufacturers will disagree with us, but a lot of accessory manufacturers would absolutely agree with us. So, and I do note that decoupled designs are absolutely fine for an underground type of cable or even a lashed type of cable. But ADSS is supposed to support its own weight. Therefore, it needs to work well with the dead ends that are going to be used on it. And yeah, it's good to have some margin for error in your design too. Okay, but what about the splice prep objections? And we've talked about splice prep, ease of splice prep several times throughout this presentation. And I want you to view splice prep objections in the context that splice prep is on the order of a few hours, and your cable operation, in contrast, is on the order of a few decades. So when there is a conflict between reliability and ease of splice prep, I think reliability should win every time. As I say here, the tail should not wag the dog. When it's not a conflict between reliability, like I really don't feel that strongly about the cable core and the issue of dry versus wet cores. Yes, I think a wet core would be slightly better, but by the time you got a jacket breach, you got bigger problems anyway. But in the case of a coupled versus decoupled design, that's a different animal. Pardon the pun about the dog. But that's a different animal because that directly relates to long-term operational performance, right? You want that dead end to work on day one, and you want that dead end to work on day one of year 20 as well. And by using a coupled design, you're helping to make sure that happened. If you're using a decoupled design, you're not. So in my opinion, when the conflict is between reliability and ease of splice prep, reliability should win. Okay, other considerations, the tubes. When a cable supplier is making tubes, they should be using a process that has continuous inline EFL monitoring and control. And remember way back, we talked that today's manufacturing processes yield consistent and well-coordinated EFL. Any good cable supplier should be able to do this. The optical core, which we've talked about, that's the tube stranded around your center FRP rod or your center element. That core should be stranded using a conservative lay length. Lay length is critical to maximize that zero fiber strain margin and minimize any fiber strain at that maximum rated design tension. Hold those thoughts for a minute because we'll come back to them when we talk about sag and tension and why this is important. The core itself should also be stranded using reverse oscillating lay, and that's when the lay direction, it goes like clockwise for a few inches and then goes back to counterclockwise and then transitions back again to clockwise and so forth and so on. And that does facilitate splice prep and midspan access. So see, I don't really hate the splice text. I am, when it's appropriate, when it's not an issue of reliability, I'm willing to try to make their life a little bit easier. Only when reliability is an issue that I get prickly. Okay, a couple more things to talk about. What about sag and tension characteristics, and when do you need to use a track-resistant jacket? So, ADSS sag and tension is quite different from OPGW or metal cables. In metal cables, you have a high thermal coefficient of expansion. So under temperature changes, they change a lot. And just in general, they weigh more, and you end up needing strength to control their sag. because as a consequence of their weight. And ADSS is much less lighter, but it's plastic, so it's stretchy. And because it's stretchy, you have under wind loading, horizontal blowout, and that has to be checked, horizontal blowout. And during ice loading, you can have substantial increase in vertical sag. And so you got to be concerned about that. And because the cable stretches much more relative to a metal cable, you have to be concerned about your fiber strain, and you end up using strength to control fiber strain. So strength to control sag, strength to control fiber strain for ADSS. Now, some people may say to you, well, you don't have to worry about ice loading on ADSS, and we'll talk about it on the next slide. And then before I leave this slide, I just want to comment that the convention in the industry is for ADSS sag to be 1 to 1.5% of span length at everyday condition. Right, so if I had a 500-foot span, I'm saying the sag should be 5 feet to 7.5 feet. Everyday tension, so no ice or wind loading. So I only have those people that argue that ice doesn't accumulate on ADSS. They have to defend their position, because all I have to do is show one picture like this that shows here's an ADSS cable with plenty of ice loading on it, and you can see how great its sag is compared to the conductors around it. And it also even looks like there's a second dielectric cable installed here that didn't get the ice loading on it, but I only got to show one. In considering your fiber strain, I said you're using your strength and your ADSS to control fiber strain. Cable suppliers have a design policy on fiber strain. Either they're not allowing it, which is the best practice, so 0 fiber strain up through the maximum tension that you would allow on that cable, and that's our policy. And we're not the only one, but some others do allow some strain, and that's low risk, or can be low risk. We'll see in a moment, it could be high risk, but the point is it's not 0 risk. Ideally, I think that you would like to not have strain on your fiber. So, but an alternative to that is that you could have 0 fiber strain at your everyday condition. So no ice, no wind loading, typical day, but limited fiber strain at the maximum rated design tension. So the point where you do have your wind and ice loading. If you're going to allow strain, the best limit is that 0.2% I talked about earlier that comes from Corning. Now, one could argue, well, Corning did their research a long time. Fiber is made a lot better today. Maybe you can allow that strain to be more and still have an acceptably low risk of failure. And there's merit to that argument. So not too bad if you let it go up to 0.3. You start to get risky at 0.4. Greater than 0.4, in my opinion, I think you're kidding yourselves. That's just gambling at that point. So there is some merit to, in today's fiber, allowing this to float up a little bit, but what's the real benefit? Okay, I make a cable cheaper, because I'm not sure you really change the size of the cable. You just use less aramid, or you use maybe a lower grade of aramid, and therefore allow the strain to go up a little bit more. I don't know. I know what I would do. So where do you actually get the data from? So you should pick what you want, and then you got to get your actual sag and tension data. With ADSS, it's very common for the manufacturer to provide charts, and you just need to make sure it covers your loading criteria. You can generate your own data, PLS CAD. You get a wire file for an ADSS cable. You can find some in their library at their website, or you can ask the cable supplier to send you a wire file. Southwire SAG-10 program is not as conducive for doing sag and tension calculations on ADSS. It's kind of set up for one particular cable manufacturer who won't go mention today, but you could probably guess who it is, and it doesn't really work well with anybody else's. Just kind of a passing note, ADSS sag charts are not temperature related because, again, the thermal coefficient of expansion is so low that you can essentially ignore it. And so that is the industry, I shouldn't say industry standard, I should say industry practice is to ignore the temperature effects. This is intended only as a primer. We'll talk about generating sag and tension data for ADSS in a separate engineering webinar. Electric fields, which is like our last big topic of the day. So a standard polyethylene jacket, whether it's medium density polyethylene or high density polyethylene, is limited to a space potential of about 12 kV. Now, PE, polyethylene, degrades in a strong electric field. So some of you are probably noticing, hey, wait a minute, you're talking about an electric field here versus a space potential. Space potential is just like the charge or the potential that exists at a point in space, hence the name space potential. But a field is the change in space potential over a distance. So it's a vector. So these aren't really the same thing. And my response to you is that you are absolutely correct. And yet this is the way it's most commonly done because it's easier, a lot easier, and a lot more practical than trying to analyze and work with the electric field. But true, it is the electric field that leads to tracking on a jacket. But when we talk about voltage, we talk about, well, I don't want to touch a high voltage line. Well, but you can as long as you don't complete a circuit. But we still talk about the voltage and use that in ways that are useful, even though what's really dangerous is the current. So what really kills you is the current, not the voltage. It's a similar concept here. The space potential is still useful to work with because that's easily known. This is a lot harder to know and work with. In any case, when you get a jacket burned through, possibly even then you've got a breach to deal with, and you can get mechanical or optical failure. That burning could actually burn enough of the strength material to cause mechanical failure or allow water, breach the tubes, allow water in the tubes or whatever, and you can get optical failure. But typically you get mechanical failure before or concurrent with optical failure. Usually you don't just see optical failure all by itself. Above a 12 kV space potential, you need to use a tracking resistant jacket. You also have to be concerned about corona at the tips of accessories because they can, even though the field is okay and you're using a track resistant jacket, a corona can damage the jacket and you still get these bad things up here. But there is a solution, corona coils. They grade out the electric field and therefore allow the cable to operate safely. When you're working, a lot of times people think that I'm pulling in an ADSS so I can do that on a live line, no problem. And that is true, but you could have induction on the pulling line during installation. So you do have to be a little bit careful about that. The maximum space potential for an ADSS cable is 25 kV. Of that, sorry, you can't use any ADSS cable. So here are some general guidelines. Oh, I probably should have changed this to space potential guidelines. Anyway. Oh, well, it's really voltage guidelines. Anyway, you'll get the idea. Up to a 35 kV line, you don't really have to worry about tracking. From 35 kV to 138, usually there's no danger. You kind of have to try to get the cable too close to the phase conductors. Maybe at 115 kV and above, you should work with the supplier, just double check and be safe on that. From 138 to 230, you absolutely should check, and the supplier should be able to help you do that. And at 230 kV and above, you absolutely have a danger, and you absolutely need to use a tracking resistant jacket and corona coils. And again, the supplier should be able to help you with that and help you with details. Here's a picture of what Corona has done in the field. And here's a picture of the Corona coils that are the solution to Corona problems. That space potential analysis that I talked about, so you need to look at it. You'll end up with something that looks like this. So what you're seeing here is the conductors. So this is a H-frame 345 kV line. This data actually came from an NCAP customer. So you got the 3-phase conductors and 2 shield wires above it. And what I'm going to try to do here, I'm not going to do it here. Actually, we're getting close on time anyway. So the white is okay. Any jacket is okay in that. The kind of pink color means you need a tracking resistant jacket, and the red color is a no-go zone for any kind of ADSS. So what you have here is like an attachment zone where you could use a tracking resistant jacket, no problem. You have a theoretical zone where you could even use a standard jacket. But notice that we're getting close to 20 feet, which, what's that, around 7 meters. And it's a 345 kV line. So the spans are probably long enough that this isn't going to work. The sag of the cable would violate your ground clearance. So that's something you would have to check, and I suspect it wouldn't work. Now, some of you are probably thinking, hey, Mike, what about this area up here? Couldn't I use that? And I'd say, yeah, you could. Now, a lot of utilities don't do that. There is a preference for putting ADSS below the phase conductors for operational and maintenance reasons. But yeah, you could potentially, in theory, you know, put something to hold the cable up here. You'd have to double check the sag, make sure you have clearance between your shield wires, and also you're not likely to have a problem with your phase conductors, but you'd want to check it. But yes, that would be theoretically possible. You need to stay in the pink, as I say. Okay. And then last thing, I've talked about rip cords throughout this presentation, and they're helpful. 2 rip cords under the outer jacket helps a lot. So that's what you see in this illustration. And this is especially true if the cable is a coupled design, like I talked about before. A good stripping tool is an option. Here are some of the ones that I've used over the years. The key takeaway from this slide is that rip cords will vary by supplier. So you need to specify exactly what you want. At NCAB, we put 2 under the outer jacket and 1 under the inner jacket. But again, remember, we use low density polyethylene on an inner jacket. We think that's good. If you were using medium density, you might want 2. And some customers do want 2 under each jacket. And some suppliers will only have 1 under the outer jacket. And some suppliers will just omit them all together. So you're back to this concept here. You need to think about what you want and then specify exactly what you want. And any supplier can do pretty much any configuration that you want, you know, anything within reason. And then just to close out, we do have on our website our advanced cable engineering system, so you can look at how you might go about actually selecting an optimal ADSS design for your project. It helps you with the accessories and doing cost estimates and planning the logistics and whatnot. And we do have a new ACES spot. I don't think that's actually on the website yet, but it will be real darn soon, where you can do your own space potential analysis and, you know, impress people at social gatherings by showing them your own space potential analysis that you generated yourself. And I appreciate everybody's time and attention today. And we now have some time for questions. And I will let my assistant Olga help me out there. Help people ask their questions.
I'm going to enable the audio settings for all attendees. So if you want, you can turn on your audio and ask your question. So here we go. And Mike, we have a question on the chat from Brian Searles. Are the empty filler tubes the same material as the fiber-filled ones? If not, do they add to the strength rating of the cable? Essentially, would using those positions with fiber-filled loose tubes affect that rating?
Oh, good question. Let's go back to talk about that because something in the category of I didn't think to talk about that. This is as good as any. It doesn't matter the cable design. So the question is, what material is used for this filler, and is that considered a strength element? The second question is easy. It's not considered a strength element. There are a couple of possibilities for using this material, or for what you would use here. One possibility is to use PBT, right? Same material as you might use for the tube. The problem with that is cost. And another problem with that is that, remember I said PBT is quite strong. So you end up with a really strong element there, but it doesn't really buy you anything. You don't use it as part of your strength calculation. And I don't have time to go into it here, but it can cause some other problems if you're not careful with how, yeah, I just don't have time to go into that in detail today. Another material that you could use is polyethylene, but you have a problem with polyethylene because when you put a jacket, extruded jacket over polyethylene, you potentially melt the polyethylene. What we're seeing more suppliers, including ourselves, do is to use empty tubes. So you would use PBT as a tube completely empty. I say completely empty. You would go ahead and either, if it's a dry tube, put a yarn in it, or use the gel in it. But I meant empty and no fibers, and that's a reasonable compromise because then you're kind of reducing cost. You don't end up with this real strong element that's adding weight and cost, but really giving you no effective benefit. So maybe next time I do this, I'll even talk about the filler rods. Hope that answered your question, Brian. Okay, other questions?
Not on the chat, but can you touch on vibration dampers for ADSS?
Oh, yeah. Vibration dampers, so there'll be a separate webinar where we talk about accessories. But the answer is really simple when it comes to vibration dampers. Vibration dampers are always cheap insurance. So arguably on, say, again, I'm the one who said, short span, don't use that. That's really too vague. But in short span distribution applications, you can argue that you don't need it, that you're not going to get the smooth laminar wind flow that you need to actually have aeolian vibration. However, the counter to that is that ADSS, being a nice, smooth, round cable, would arguably be more vulnerable to getting wind-induced motion than a metal cable would. So I end up in the realm of spiral vibration dampers are cheap insurance and should always be used regardless of the span length. The short, medium, long, they're easy to install, they're not expensive, and they're a form of, as I say, of cheap insurance.
How can we get a copy of this presentation?
What will happen is that everybody who registered, Olga will be sending out an email. There are a couple things to note about the email that you'll get. One is that it'll come with a survey, and we ask, please give us feedback. You know, if it was good or if it was bad. things I didn't cover, things that are wrong. You know, I'm a reasonable guy. If you think I'm wrong on something, I'll listen to you, hear you out. And if I get new information and I learn something new, I'll change my presentation accordingly. So give us feedback. The second thing is that you'll get a contact where you can get the slides. On our website, a recording of this will be posted. We always post them there. So, you know, if it's late one night and you can't sleep, you can always pull up a micro or other in-cab webinar to watch. There'll also be a link, something I said I would talk about, and I'm using this question to remind me to talk about it, is how do you get your continuing education hours credit? And the way you do that is there'll be a link to go take a test. It's 10 questions, pretty simple stuff, basic stuff from the presentation. And if you score 70% or more, we report that to RCEP, and they in turn will give you the credit hours for that. So again, I hope I answered that question well. Wait for the email link. If for some reason you don't get an email link, you can reach out to us. Olga, is the address webinar@incabamerica.com?
Correct, indeed. I will be following up. Yeah, I will be following up all attendees if I have an email from them. But anyways, you can use that email to send your request, and we will be answering immediately, almost.
Real darn fast, if not immediate. Okay, any other questions?
Excuse me, I have one question.
Sure.
Regarding the effective pollution index on the ADSS cable.
Yeah.
How this value affect the different design of ADSS cable, and how it can be used to decide it if the ADSS cable is suitable for a certain environment. For example, in Gulf area, it is difficult to use the ADSS cable due to the environmental condition.
Yeah, that's a good point. That's like way above the scope of this presentation, but I'll give you a general answer. So the pollution index should only be a concern if the cable has an anti-tracking jacket. So if you were just in a distribution environment, pollution really shouldn't affect the life of your cable per se. I mean, unless it's, I guess, highly acidic, in which case you've probably got other problems to deal with, just other than just your ADSS cable, I would suspect. But so if you've got a tracking resistant cable and you put it in a highly polluted environment, it's like how insulators work. So my conceptual answer to you is think about what you do for your insulators. If you have a power line and insulators are having trouble because of pollution, your solution probably is that you have to go clean them every so often. If you wash them every year, every 2 years, whatever. And so it's not just the pollution, but it's also that the pollution has accumulated. And certain parts of the country, you have a natural, there's enough rain to kind of naturally wash the pollution off. And then in other areas, there are not. And so when you have problems with insulators because there's not enough natural cleaning of the pollution from just the rain, you have to go wash the insulators. Well, that would be my solution for the ADSS. If I was having a problem, I'd also go hose down the ADSS to clean it as well, because in that sense, a tracking resistant jacket is very parallel in how it operates to how an insulator operates. So if you're having trouble with your insulators and you're thinking about installing track resistant ADSS, you're likely going to have problems on your track resistant ADSS. Conversely, if you don't, you're probably not. Does that help?
Yes, but I think this means also you might decide that the ADSS cable is not suitable to be installed in Gulf region.
I'm sorry,
Because there is a
there's so much background noise, I can't really understand what you're asking
no.
me.
Can you hear me again?
Yes, perfect now.
Yes. Regarding, as you are aware, according your reply, maybe a rain can be considered as a cleaning to the ADSS cable. But in
Yes.
case of Gulf area, it is a very rare to have a rain here. Does this mean that ADSS cable, even with a special design, is not recommended to be installed in Gulf regions or Gulf countries?
Well, yeah, short answer, yes. If you're in a region where you know you don't have natural cleaning, but you do, and you know you have enough pollution to potentially cause a problem, then yes, your option then would be to not use ADSS, which therefore means use OPGW or use a buried cable or another metal cable. So there are other metal cables that are potential solution. It depends upon the details, but the other metal possibilities are potentially you could use an optical phase conductor. That's a possibility. You could use an optical neutral, which is kind of a variation of the optical phase conductor theme. You could use an optical messenger wire, like if you have a metal cable that maybe other cables are lashed to. That's something that you see in the United States. I don't know about your area of the world. Or you could go underground. And then the other possibility is that what I was trying to say is that some utilities in the United States have problems with their insulators because of pollution and contamination. And what they do about that, again, some utilities, what they'll do is they will go out once a year or so and wash their insulators. I mean, like a big fire hose type thing, just to clean up the pollution. And so what I was saying is that if you're already doing that and you want to use an ADSS, well, yeah, in theory, you could use that fire hose and clean your ADSS while you're cleaning your insulators. Not saying I would necessarily recommend that, but it could be done. And here's another opportunity for me to get my biases out into the open. I come from a metal cables background. So if you asked me and it was a transmission line, I wouldn't use ADSS. I would then go to a metal cable, specifically OPGW, if I could. I hope that helps.
Yes, this is help a lot. Sorry, I have my last question.
Sure.
If some vendor or manufacturer study the region and mentions that I can produce a cable that can, ADSS cables that can survive under this environmental condition, do you think, and he make, by the way, the dry band arcing test as per IEEE standard 1EEE. Do you think we can agree with his product and we can try it in the Gulf region, or it is risky?
My take on what you've told me, because I don't know any of the details, my take on what you told me is that that's very risky. And so then your response is a couple possibilities. One is that you could say, okay, are you willing to give me a 5-year warranty on the cable if there's any problems? Maybe
We
even
put
10-year warranty.
He agreed. Yes.
So, but I can't speak to a lot of the particulars there, but I will tell you one thing that says a red flag in my mind is the dry band arcing test that they're referring to. I would say, okay, let me see your dry band arcing test report. And I would scrutinize that report very carefully. Who did it and where? Because in the United States, that test was often done at one particular lab at Arizona State University. And the professor that developed that test and was doing it has long since retired, and I don't know who's picked up the mantle on that. Is Corinne Dimnick, I see you on. Are you able to comment on that? Do y'all do that test? Would y'all be able to do that test? Please feel free to weigh in, Corinne. And another person that I see on here is Joe Renowden. And Joe, I welcome you to chime in as well too, because we're here to share information. So I welcome others to share on this point. But Mustafa, I gotta say, I'm an old Army guy and I'm cynical and about everything. So when somebody comes to me and tells me something is too good to be true, I look at it very closely. But Joe, you're trying to speak, so please.
Hi, Mike. This is Joe Renowden.
Yeah, come on. What's your thoughts, Joe?
Well, actually, I was going to ask you that same question about tracking in a contaminated area. I know in coastal Florida, we had installed quite a bit of ADSS, but I've been retired for 20 years now, so I really don't know what the long-term results have been. So if there's anybody else on from Florida Power and Light, or in fact, some of the Gulf Coastal companies, they might be able to provide some experience with that. But that was literally a question that I was going to ask you.
Okay. But as I recall, when you were still working at FPL, y'all had a fair amount of problems with ADSS and high contaminated environment, yeah?
Well, it wasn't really from contamination, external contamination. There was a very unusual problem we had with ADSS under a 500 kV line that had to do with the rinsing of the Kevlar fiber. Apparently, DuPont didn't have a specification to rinse. They used to rinse it in an acid, or they produced it in an acid and they rinsed it in something else. But the rinsing was not standard, so there was a highly variable amount of conductive salt from the acid left. And one of the things that happened with us is, in that very high humid environment, we ended up getting water vapor permeating through the jacket during the day, and then it would condense at night, and so over time there was a buildup of moisture inside, and the Kevlar became conductive. And in the electric field that it was in, under the 500 line, the Kevlar fibers actually, fiber by fiber, burned. They burned open. There was enough microamperes in there to burn those fibers open, and eventually enough fibers broke where it lost its tensile strength, and it stretched and sagged down and failed. That was a very unusual problem. It hasn't been reported in anybody's literature or anything, but that was, good Lord, that was 30 years ago. So I don't think it's very common. So it was an internal contamination problem, not an external one.
Mm-hmm. So do you agree with my assessment that I would use insulators as a surrogate for how the ADSS would be likely to perform?
Oh, sure. With the insulators, there's a lot of different polymer compounds out there, and a lot of them are pretty good. And the thing that tends to really deteriorate the insulators is the high electric field, around where it's attached to the conductor. It's a much higher electric field than you're going to be putting ADSS in. However, my concern would be, in a contaminated area, would be the the tracking that might occur in the vicinity of the end of the metal heliform grips.
Right, but that's solved with corona coils.
Yeah, that eliminates the corona. But you know, at night you get condensation and whatever contaminants are there maybe get more conductive.
Oh.
And that's more of an open question because, as I mentioned earlier, I haven't heard of that kind of deterioration taking place, you know, but I've kind of been out of that loop for almost 20 years now, that, you know, that connected to what's going on with ADSS fiber, especially in humid, contaminated environments like coastal areas, and especially in the Gulf of Mexico coastal area. But I know that there are similar areas all over the world.
Okay, well, thanks for sharing your experience, Joe. And back to Mustafa, I think your question is a little bit too broad for what we're talking about today. I'd be glad to follow up with me, because if we look at the particulars, I might be able to give you some more specific thoughts as to whether I think it would be okay or not. And some thoughts about how, I mentioned I would proceed with great caution, and I could share with you some specific people to talk to, like Joe Rinaldo. Another person would be Monty Teominen, Corinne Dimnick at Connectrix at Test Lab. They could talk to you about doing some testing to verify it. I would just proceed with caution as a general principle, and then I could give you some pointers on how you could actually implement that proceeding with caution. So how's that?
Okay, thank you very much. I appreciated your feedback. Thank you.
You're welcome.
Hey, Mike,
Yeah.
Mike, it's Joe again. Are you still on the ADSS standard committee?
Yes.
I'm wondering if there might be some way to get someone or folks to contribute any experience with those kind of things. Maybe people on the standards committee might be connected to people who might have had that kind of experience.
That's a good point. And agents like the UTC maybe, or EPRI, could do some surveys to maybe draw out utilities experience with that.
Yeah, that's a good thought. An EPRI survey, or even an EEI or a Southeast Electric Exchange survey might produce some really, really useful and valuable background experience.
Yeah. Okay.
Okay.
We had some other questions. I saw somebody. I guess I need to find chat. Aha. Chat. Let's see. Let me go back to the beginning.
Mike, I can help you. So Norbert Fink is asking, do you use ADSS as emergency cable in the US after floodings, etc.?
Yes. That was the question I saw flash up. Yes. Short answer, yes. Do I need to elaborate on that? I mean, it's it can be something that you can get quickly and get installed. Obviously, you could lay it on the ground to get started with. You wouldn't want to leave it that way, but that could be something that you could do as a short-term solution while you're working to get transmission towers repaired and other circuits put back in service, and as a quick solution to install communications immediately, and then maybe do something that's more permanent later as time permits.
Yeah, thank you. This was exactly the question, the quick installation and to have in emergency cases a solution, because we had now the floodings here in Western Germany, which we never experienced before, and ADSS may be a solution for this.
Yes,
Thank you.
You're welcome. I would absolutely use them in that condition. Obviously, you got to apply some common sense. I think I mentioned earlier in passing that I'm an old Army guy, and I was specifically a signal corps guy. And I was in the Army at a time, we were still using muskets when I first joined. Just kidding. Just a joke. But we were using wire for field phones. And in the field, when an Army unit was deploying, well, you might have roads there. And so we would deploy this wire, and kind of depended upon how much traffic you had on a road. If you had to cross a road, if it was a low traffic, you might just stake this wire on both sides of the road and allow it to be driven over. And but if it was heavily traveled, or you were expecting things like tanks, well, then we would use some poles or sometimes cut trees and string it so that it was an aerial crossing of the road. So with ADSS, you could just lay it on the ground, and then if you have to cross a road, well, maybe do it someplace where there's a bridge, so you're not actually crossing at grade, or maybe use a drop cable, flat drop cable if there's light traffic, or again, you improvise something to get an aerial crossing. But yeah, absolutely, it's a good temporary solution to get communications restored and buy you time to do something more permanent later.
Yeah. Thank you.
You're welcome. Any other questions? Kind of like last call. All right, I appreciate everybody's attention, and the guys that are still here. You guys are the real hardcore tough ones, I guess. So let us know how we can be of further service. You've got somewhere on here our contact information. I see the webinar thing was there at the beginning. I think I had my email address. Let's see. Okay, well, mine is just mike.riddle@incapamerica.com. So do feel free to reach out to me. You can also find my contact information on the INCAP America website. And I welcome you to reach out to talk about us, especially you, Mustafa, to talk about the details of your challenges that you face. Be glad to help. And then Norbert, if I can be a further assistant, please feel free to reach out to me as well. Thank everybody for your participation, and hope you enjoy the rest of your day. Thanks a lot.
Thank you, Mike. Thanks, Mike.
Thanks, Joe.
Excellent and very valuable presentation, as always.
Thanks,
Thank
Joe.
you very much.
Coming from you, that's high praise. I really appreciate it. Bye, y'all.